Hello, I am Chun, a PhD student from KAIST. Today I will present attributed hypergraph generation with realistic interplay between structure and attributes. Group interactions are everywhere. First example is co-authorship of researchers, where researchers interact as a group for a publication. Second example is online group chats. People talk in groups in online apps, such as Messenger or Slack. Third example is a reviewed item set. A group of items that are reviewed by a user on platforms such as IMDb or Amazon can be viewed as a group interaction. Real-world group interactions can be naturally modeled through hypergraphs. Hypergraphs model group interactions among individuals or objects through hyperedges, which is a subset of any number of nodes. For example, a co-authorship network can be viewed as a hypergraph, with authors as nodes and publications as hyperedges. In real-world hypergraphs, hyperedges aren't just randomly formed among nodes, but instead formed in a systematic and realistic manner. Thus, various hypergraph generative models have been proposed to explicitly incorporate the underlying mechanism in hyperedge construction. For example, in real world, hyperedges densely overlap with each other, and hyperlap is designed to reproduce this dense overlap. These hypergraph generative models can be utilized to many data mining applications, including community detection and hyperedge prediction. At the same time, many real-world hypergraphs include node attributes. An attributed hypergraph includes node attributes which describe the properties or characteristics of each node. For example, in a co-authorship hypergraph, where each node corresponds to a researcher, information such as his affiliation or main field of research can be node attributes. These attributes can be expressed using attribute vectors. In this work, we use binary vectors since we can convert other types of node attributes to binary. We can apply thresholding and one-hot encoding for continuous and categorical attributes respectively. Node attributes may influence the connection between nodes, and moreover to hyperedge formation. As in the example of co-authorship hypergraph, researchers with same affiliation and same main research field are more likely to write a paper together. Also, in real world, homophily, a phenomena of similar nodes attaching frequently with each other, is prevalent. Thus, we can think there is a noticeable relation between structure and attribute in a hypergraph. Although node attributes contain valuable information about nodes, which can influence hyperedge formation, most existing hypergraph generative models overlook node attributes. They are structure-based and considering only the structural role of nodes. Thus, we propose NoAH, a node attribute-based hypergraph generator. NoAH produces realistic hypergraphs using node attributes. We also propose a parameter fitting algorithm, NoAHFit. Through experiments, we show that our model outperforms existing hypergraph generators in capturing structure-attribute interplay. And also, our model is scalable with respect to the number of hyperedges and attributes. Next, I will introduce the preliminaries of our work, including a key preliminary model MEG, and metrics to quantify the interplay between structure and attributes in a hypergraph. There are several attribute-based models for pairwise graphs, particularly multiplicative attributed graph. In short, MEG model aims to capture how node attributes affect edge formation in pairwise graphs. For each attribute dimension, MEG defines an affinity matrix, quantifying edge formation probability based on attribute value pair. So, for this example, there are theta 1 through theta 4 for 4 dimensions, where theta 1 denotes affinity matrix for attribute dimension 1. MEG model extracts entries from the affinity matrices based on attribute value pair. For the first dimension, where node U has attribute 1 and V has attribute 0, the corresponding affinity value 0.5 is chosen. Next, for the second dimension with node U having attribute value 0 and V having attribute value 1, the corresponding affinity value 0.3 is chosen. In the same way, from theta 3, 0.9 is chosen, and from theta 4, 0.8 is chosen. The MEG model calculates the edge probability between two nodes as the multiplication of entries from the affinity matrices. Thus, the probability of node U and V being connected is multiplication of 4 entries, which is 0.108. Formally, the probability can be written in this form, with node attribute dimension k and x denoting the node attribute vector. Next, I will explain the measures for quantifying the interplay between structure and attribute. Recall that the node attribute may influence hyperedge formation. Now, how can we quantify the interplay between structure and attributes? In this work, we utilize 3 measures, which can be categorized into first, hyperedge level measures, which measures how node attributes are distributed within a hyperedge. Second is node level measure, which quantifies the tendency of nodes to form hyperedges with other nodes of similar attributes. The first measure is type S affinity ratio scores. Type S(T) affinity ratio score quantifies the significance of a particular attribute value appearing exactly t times in a size S hyperedge. For attribute value V in dimension D, the type S(T) affinity ratio score is defined as the normalized frequency of D, V nodes in S(T) hyperedges, where the D, V nodes are nodes with attribute value V in dimension D, and S(T) hyperedges are hyperedges of size S with exactly T nodes of value V. To help understanding type S(T) affinity ratio score, I will explain with type 3,1 affinity ratio score for value 1 in dimension 1, which is the normalized frequency of 1,1 nodes in 3,1 hyperedges. Here, 1,1 nodes are nodes with value 1 in dimension 1, which is highlighted in green, and 3,1 hyperedges are size 3 hyperedges with exactly 1 node of value 1 in dimension 1, which is highlighted in purple. Thus, the type 3,1 affinity ratio score is calculated as the normalized frequency of this red highlighted case. For details, please refer to the paper. We can generalize this for any attribute dimension and any t, where a high ratio score means homophily, and the low ratio score denotes an anti-homophily. We denote type S(T) affinity ratio scores from t equal 1 to t equal s as type S affinity ratio scores. We consider hyperedges of size 2, 3, and 4, since most hyperedges in real world are small sized. Next is hyperedge entropy, which aims to quantify the hyperedge level attribute homogeneity. From a work of Lee et al., in real-world hypergraphs, hyperedges show homogeneity for node labels compared to the randomized cases. Note that the node labels are also a type of node attributes. Hyperedge entropy is defined for each attribute dimension. For this example, we can calculate the entropy for attribute dimension 1, dimension 2, and dimension 3 respectively. Moreover, Lee et al. Observed that the label homogeneity in real-world hypergraphs holds even after propagation steps between incident nodes and hyperedges. Thus, we also measure higher-order hyperedge entropy, measuring the hyperedge entropy after multiple rounds of attribute propagation. The propagation is done by first calculating the hyperedge attribute from the previous node attribute. Hyperedge attribute is calculated as the average of node attributes within a hyperedge. Then, the propagation is done from hyperedge to node. Next, node attributes are calculated as the average of hyperedge attributes that the node is contained in. Higher order hyperedge entropy is calculated as the entropy after this multiple rounds of attribute propagation. Node homophily score measures the node-level interplay between structure and attribute. Node homophily score is measured for each node and each attribute dimension. Let's look at this example with respect to node V. Node homophily score measures the ratio of incident nodes with same attribute value. Here, for node V, first hyperedge includes one neighbor with same attribute, so it is added to both the numerator and the denominator. For the next hyperedge, there are two neighbors, and since only one of them shared the same attributes, we add it to the numerator and denominator accordingly. Thus, the node homophily score for node V for attribute dimension 1 is 2 over 3. Similarly, we can compute for attribute dimension 2 and for dimension 3. Now I will explain our proposed model NoAH and fitting algorithm NoAHFit. We propose NoAH, Node Attribute-Based Hypergraph Generator. NoAH aims to generate realistic hypergraphs that capture the interplay between structure and attribute observed in real-world hypergraphs. NoAH is built on three key ideas. First, NoAH models hyperedge formation based on node attributes. This enables NoAH to capture the interplay between structure and attributes. Second, in NoAH, nodes are splitted into core and fringe nodes. Let's recall the example of co-authorship hypergraph. Here, certain nodes, such as the corresponding author, can act as a core node, meaning it plays a central role in hyperedge formation. Thus, in NoAH, nodes are splitted into core and fringe nodes, which are distinct with each other. This allows NoAH to capture hierarchical structure prevalent in real-world hypergraphs in a simple yet effective manner. Note that the core nodes will act in a more important manner during hyperedge formation step, as we will discuss soon. Finally, NoAH models each hyperedge formation as a series of attachments. This incremental construction reduces the computational complexity of NoAH. NoAH generates each hyperedge through a two-step process. The first step is the core group construction step. First, from the core node set, NoAH selects a seed core node based on the seed core probability distribution, p-seed. Then, other nodes attach to the seed core node based on the mag-style probability. In NoAH, we separately define affinity matrices for core and fringe nodes. In the current core group generation step, the attachment probability is calculated based on the core affinity matrices. Next is the fringe attachment step. Based on the constructed core group, NoAH first collects the set of attributes from the nodes in the core group. Then, we perform attribute-wise sampling for each fringe nodes. Here, 0, 1, 1 is selected for each attribute dimension 1, 2, and 3. We repeat this for all fringe nodes until we obtain all the mixed attributes. This allows all nodes inside the core group being able to influence the fringe attachment step. Using the mixed attributes and attributes of the fringe nodes, we calculate the fringe attachment probability also in mag style. Here, the fringe affinity matrices are utilized. Based on the calculated probabilities, the hyperedge is completed by attaching the fringe nodes accordingly. By repeating this step m times, we can obtain a hypergraph with m hyperedges. An important characteristic about NoAH is that the probability of each hyperedge being formed can be parameterized through NoAH. Thus, we propose NoAHFit, a method for tuning the parameters of NoAH to the given hypergraph. NoAHFit enables NoAH to generate hypergraphs that closely resemble the input hypergraph in both structure and attribute patterns. This is useful for downstream applications including community detection and hyperedge prediction. NoAHFit updates each parameter through gradient descent, aiming to maximize the likelihood of a given hypergraph. Here, the likelihood of a given hypergraph is the product of the likelihood of each hyperedge, which is directly modeled by NoAH. Now, I will move on to the experiments section. We tested 8 baseline models on 9 datasets from 4 different domains to compare the effectiveness of NoAH. Moreover, we also utilized a variant of NoAH without the core-fringe node hierarchy. We used 6 metrics that we have previously introduced to evaluate the similarity of structure-attribute interplay with the target hypergraph. Type S affinity ratio scores quantify the fine-grained patterns in hyperedge attribute distribution. Hyperedge entropy quantifies the coarse-grained patterns in hyperedge attribute distribution. And finally, node homophily score quantifies the node-level patterns of attribute distribution. Here we show the results with Amazon Music dataset. For 6 metrics, we present the difference with the original hypergraph, and AR denotes the average ranking for all metrics. Including the Amazon Music dataset presented in this slide, NoAH outperformed all baselines and the variant NoAH CF for 6 datasets. Overall, NoAH shows the best performance among all baselines. This shows that NoAH can capture the interplay between structure and attributes better than other hypergraph generative models. Moreover, the comparison with the variant shows that the core-fringe structure is crucial for the performance. Additionally, we have conducted a case study comparing the ground truth hypergraph with hypergraphs generated by NoAH and HyperCL. We focus on the first attribute in the Amazon Music dataset. Here, the gray boxes indicate the scores for original hypergraph, and blue and red boxes each indicate the scores for the hypergraphs generated by HyperCL and NoAH. First, NoAH produces similar trends for type 4 affinity ratio scores with respect to the original hypergraph, capturing how node attribute is distributed among size 4 hyperedges. Next, NoAH produces similar distribution for hyperedge entropy with respect to the original hypergraph, capturing the hyperedge level attribute homogeneity. Finally, NoAH produces similar distribution for node homophily score with respect to the original hypergraph, capturing the node level attribute homogeneity. Also, from the skewness of hyperedge entropy towards 0 and node homophily score towards 1, we can see that the current attribute exhibit a strong homophily. And the affinity matrices estimated by NoAHFit captures this phenomena, having large values for the diagonal entries which model the edge formation weights between nodes with the same attribute values. Here, the results show that the diagonal entries are larger than the entry for 0-1 pair, modeling the homophilic characteristic. Also, we show that NoAH and NoAHFit is scalable with respect to the number of hyperedges and attributes. Now I will end today's presentation with some conclusions. We propose NoAH, a stochastic model for attributed hypergraphs that produces a realistic interplay between structure and attributes. We developed NoAHFit, a parameter fitting algorithm for NoAH that captures the relationship between structure and node attributes in a given hypergraph. We empirically demonstrate that NoAH outperforms 8 baseline hypergraph generative models. Thank you for listening to the presentation. These are the list of references used for the presentation.